Hi, today I will present Neural Robot Dynamics or NERD. The paper studies run dynamics models for articulated rigid body robots. The paper argues that many existing neural robotics simulators need application-specific training. Also, they directly map state and control actions to the next state. If the environment is not encoded, the model must implicitly memorize it. If controller actions are used as inputs, the model tends to overfit to the training controller. As a result, generalization breaks under new tasks, new environment setups, or customized controllers. So, NERD is their answer to that generalization problem. The first idea is a hybrid prediction framework. Instead of instead of running the or simulator end to end, they only replace the parts that are application agnostic. Specifically, they target low level for dynamics and context solvers. The second idea is robot-centric and especially environment state representation. This means to stop the model from tying itself to absolute world coordinates. With those two ideas in mind, let's briefly record the classical simulator pipeline because NERD is designed around it. In a classical robotics simulator, several steps happen every time step. First, collision detection identifies potential contexts and produces context information. Next, a low-level controller converts commands into joint space torques. Then, forward dynamics and context solvers compute how the robot state changes. Finally, time integration produces the next state. Nerd perspective is simple. Many of these intermediate computationally already exist and are reusable. So the next slide shows exactly what node replaces and what it keeps. Here's the key shift. Node does not try to run collision detection or scene management. Instead, it replaces only the server-side components for the dynamics and context solvers, and it changes the model inputs. Rather than feeding controller actions directly, it uses intermediate simulation quantities that includes the robot state, joint space torques, and importantly, context-related quantities. Conceptually, context-related quantities are how they include the local environment's effect on the robot. Now that we know the overall structure, we can define the exact state and training target. So about the robot state, it includes base position. It includes base orientation represented as a quaternion. It includes joint angles. Then it includes base spatial twist. Spatial twist is the part that often causes confusion. It is not rotation. Spatial twist tells you how fast the base is moving and turning. Concretely, it is a 6-number velocity. 3 numbers for linear velocity and 3 for angular velocity. Finally, the state includes joint velocities. Now, what does NERD predict? It predicts the change in state over one-time step, not the absolute next state. Training minimize mean scared error on that state changes. Importantly, context is not separate provides target here. Instead, context enters through the input representation, which we'll look at next. So, how does NERD include context? It uses collision detections to build contact-related quantities. The robot has a set of pre-specified contact points. For each point, the simulator provides geometric contact event information. This includes the contact normal at the contact distance and the matching point on the environments. The distance convention is important. If the distance is zero or negative, that indicates collision. They are set of practical robustness tricks. Masking. If a contact point is far enough away, they zero out that contact input. The threshold is fixed across experiments. Um, it is whichever is larger, 4 times the contact thickness or point 0.1. This way, the model sees meaningful near contact signals without being flooded by irrelevant far contacts. Now, even with good contact inputs, you can still lose generalization if the representation is word frame dependent. Here's the second core idea. They explicitly enforce spatial environment under translation and rotation around the gravity axis. Practically, they do this by expressing base related state and contact quantities in the robot base frame. They also include the gravity vector, but expressed in that same base frame. There's one subtle but important choice about the output. They express the predicted state changes in the base frame at the current time step. They do not use the next time step's base frame. The reason is straightforward. If you always express motion in the robot's own next frame, base motion can become trivial or even collapse towards zero. That or that would prevent the model from learning meaningful base movement. With representation settled, the next question is time stepping. Classical simulators often use many sub-steps. Node handles that differently, which is the topic of the next slide. In many simulators, one visible time step actually contains multiple internal sub-steps. Sub-steps improve numerical stabilities, especially with contact. Common round approach is to predict acceleration at each sub-step, then integrate. Node takes a different route. It predicts the state change over the entire macro time step directly. That lets them use fine-grained simulator data during training, but it keeps inference efficient at test time. The first experiment tests long horizon stabilities using passive motion. They set joint torques to zero and just roll out dynamics. The robots used in test are cardboard, Franca, ant, and animal. Second is contact generalization. They randomize the planar ground configuration under a double pendulum. This changes when and how contact occurs. It also changes the motion mode. Some routes are contact-free and chaotic. Some involve sliding contact, some stop due to collisions. They test 7 ground setups in total. They also test fine-tuning on real-world data using cube tossing. They report that fine-tuned node reduces both position and orientation errors compared to warp. The fine-tuning converges in fewer than 5 approaches. But they have not tested humanoid scale systems with very high degrees of freedom, and random sampling may become inefficient and as dimensionally close. And fine-tuning assumes access to full state and environment setup, while real data is often partially observable. It is mentioned in papers limitation and is their future works. Thanks.